My name is Yoshiki Ohshima, and yeah, thank you for inviting me to the workshop. And I'm a computer guy, and my projects tend to be interactive, visual, collaborative, like end-user-oriented, and live programmable. So my research interest basically overlaps significantly with the area that paint covers, no pun intended. And so I'm going to talk about sort of the projects I have done, and also much more about the ideas behind those projects. And yeah, I'd like to give you some different ways of looking at things, but also first and foremost, yeah, just like sit back and relax and enjoy my talk. And so before getting into the main part, I'd like to mention the tool I am using to do this presentation. And this is called Croquet Greenlight. And it is a 2D collaborative software, like it's an infinite canvas, like where you can embed like other web pages and other contents. And actually, Marcel here is in the same room, so he's moving his cursor. And oh, I should do this, actually. Let me do this. So we are seeing the exact same thing on his computer and my computer. Oops. Oh, please don't. And so you might think that this is like Miro, and what's the big deal? But this is a little bit more interesting than Miro. So for example, I can resize, hey, and Marcel, can you move the window? And we can do this. And you cannot do this in Miro. In Miro, for example, you try to move something, and you release, and 1 second after, it changes on the other screen. So when I talk about real-time collaboration, this is the kind of things I'm talking about. And so this is, so as a part of my yeah, this network is a problem here. Yeah, if you are watching like some anime here, don't do that. Okay, this is not great. Half-working network is worse than like not working network, right? So okay, let's try to do So anyway, so I was so this is a part of self-introduction, and I was a student at Tokyo Institute of Technology, and I was supposed to be studying like compilers and object models, but I was sort of stuck, and I started procrastinating, and I found an open source programming environment called Squeak, so I just started playing with it. And one of the things I did was to port the virtual machine of Squeak to Zal's PDA. It's a little small. And oops. So back then, like this, around this time, Japanese used to make the best electronics gadget in the world. So the combination of sort of the very high-end PDA and this malleable and the multimedia-rich programming environment, that combination got some attention from the Squeak team who was at Disney. So I end up with doing internship at Disney and later hired as full-time. And the first project I did was PAX PDA, and I'm not going to talk about this here, but you can, if you are interested, you can read the paper and other talks. But by the way, this web page looks like amateurish page, but this is actually collaborative software. So Marcel, can you scroll the page? And it scrolls. And so if you want to join, scan the QR code, do it. It should be, hopefully, you need to be brave to do this kind of stuff. And anybody can scroll. So yeah, so that's instant collaboration is another thing I'm interested in. So the Parks PDA, as I said, there's a paper, and the device looked like this. But I'm not going to talk about that. But through this work, I got to know Alan Kay. And of course, everybody here knows who Alan Kay is. So he's one of the biggest visionary and the pioneers of the computing field. And he is known as the father of personal computer because he, among many other things, he conceived the idea called the Dynabook. So in 1968, when computers tend to be a big thing, like occupy like entire floor of a building or stuff, but he foresaw that Moore's law would enable like enough computing power to fit behind a flat panel, and the people will carry that kind of device around. And and he made a mock-up like this. But many people often don't understand his bigger idea. So many people thought that Alan was talking about hardware, and that's it. So sometimes people said that when iPad came out, iPad fulfilled Alan Kay's vision, Dynabook, but it wasn't. So Alan's idea was what kind of new services the computer would provide, and what kind of changes that will bring to the society. So if you look at this picture, this is drawings he did in 1968. And if you look at, so because of course those children are carrying around portable devices, but if you look at those screens, they are looking at the exact same thing, like Marcel and I are doing. And they are playing a multi-user space war game here. And not only they are playing that, actually they made the program by consulting online library and talking to teacher. So they made the game together and playing together. And so that's the future he wanted in 1968. And Alan Kay wasn't just talking. He decided to make it real. So the technology to make a portable device wasn't there, but he made an interim Dynabook and get children to program, and they are having fun. So he did that, and I said that I sort of got to know him. So this is me, this is my wife, and this is Alan Kay. So around that time, there were some other visionaries, and one of those was Douglas Engelbart. And of course, you know him. But one thing his group did was to present the collaborative structured document editing and all those things, the mouse. And it's called the mother of all demos. But of course, it wasn't called the mother of all demos when he did it. So he was showing the mouse, like a structured collaborative document editing, and like a video chat, and talk to somebody and do stuff together. So again, people often think that, Douglas Engelbart, he invented the mouse. But Douglas Engelbart's idea was also much, much bigger. So this was like the 1960s. And that's when the Cold War was upon them. And people worried about things like, maybe everybody will be dead, and maybe next week. So that's sort of in the air of the world. So Douglas Engelbart was very concerned with the future of humanity. And he thought that the better organization of people helped by education and technology and make a better system that would augment human intelligence. And that's the way to solve bigger problems that one person couldn't solve. So he wanted to augment human intelligence to solve bigger problems. And So this is sort of the interesting picture. So here's a mouse, and this is Doug, and another mouse. So interesting thing to notice here is that this is a collaborative software, but they are using it even when all collaborators are in the same room. Today, if you want to collaborate with somebody remote, you have get-go tool, maybe Zoom or Google Meet. But you are not going to use Zoom when your collaborator is in the same room, because Zoom does not augment your intelligence. It just lets you talk and maybe share screens. But this was their day-to-day, everyday working tool, and they used it. So by the way, this is Doug and this is my wife. And so their work was funded by government funded. There was a government funding agency called ARPA IPTO, and the JCR Licklider and Bob Taylor were two of the directors. And so in 1960, Licklider wrote this paper, Man-Computer Symbiosis, and he was talking about what's the future relationship between human and computer. So this was 1960, so he was one of the early thinkers of this domain. And later, Licklider and Taylor published a paper titled The Computer as a Communication Device, and this was 1968. And there were a few interesting pictures in it. So one picture was like this. So one person is presenting like the design, his design of bridge here, but others weren't just listening. They would be like checking the material strengths, or maybe some others actually wrote simulation and running it. So this image, this drawing obviously was influenced by Engelbart's work. But so this is sort of what they wanted. And another interesting picture in the paper was this. So this is an AI agent, and it's an inside joke, but it's named Oliver. And this is intelligent enough. So when insurance salesman came, this device figured out and say he's out. So that's sort of already in people's mindset in 1960s. So those are sort of the historical part I wanted to touch upon. It's coming back to the later part. But one more thing about something else before I get into like demos. And when I was invited to this cryptic acronym workshop, the two words, abstractions and notation, got me thinking about this. And I'm going to talk about like designing abstraction and notation. And when you are designing something, it's often good to think about the extreme cases, and then you get to a better feeling of the domain and where is the center and where is the boundary. So I want to talk about that a little bit here. So what came to mind was Maxwell's equations. And Maxwell had many different versions. Like this one happens to have, I think, 12 equations in it. But himself and his collaborators and actually the successors of him it took for them like 30 years to get to this 4-equation version that we know as Maxwell equations today. So it was a long process, and even Maxwell himself didn't finish it. But so this is cool, like the divergence of electric field is created by a charge and basically time varying the magnetic field creates the curl of electric field, and et cetera, et cetera. You don't have to know this, but probably you know. But why do we stop at 4 equation version? And there's a thing called bivector in geometric algebra. And basically, bivector is a compound quantity, so internally there are structures in it. But then you can define operators on it, and that's the right thing. And with that setting, you can reduce those 4 equations into one. And it looks like this. Basically, the F here has like an E part and B part. And the nabla here is a gradient operator. It's a 4-dimensional gradient operator. So you can do this. But then, we need to go to the extreme case. So why do we stop at equation that describes only the electromagnetic field? And actually, I know the formula that describes everything in the physical world. And that looks like this, U equals 0. So but the problem is that I have no idea what's in U. And of course, nobody does. But another bigger problem is that even if somebody comes up with a plausible U, that is not going to help us to write programs. The stuff we would like to write about is not going to be described by this. So abstractions have an interesting notion. And by the way, how many of you have heard of geometric algebra? That's cool. And actually, so I was watching yesterday's video live, and Hamish Todd was talking about that. So maybe you have heard of it yesterday. I did not know about this until 1 year ago. But my high school kid actually came to me one day and said, "Hey, Daddy, do you know geometric algebra?" And I say no. And my kid said, "Oh, let's watch this YouTube video together." So that's how I got to know this. But anyway, so I'm not going to turn this talk into a mathematics lecture. So I'm not going to explain all things, but those are sort of more down-to-earth things we might write in our programs. And some abstractions work very well. So quaternions, only thing you have to know is there's an operator, and you don't have to go up and down the different abstractions. But vectors, often you do want to look inside and what's there and go up and down the different levels of abstraction. And the notation, if you are designing a notation, your notation should help the fluid motion of moving up and down. So you do not want to write this horrendous kind of stuff, but rather, if it's a plus, you use plus. If it's a multiplication, you do this kind of operators. And your syntax or notation should allow going up and down. So that's what I thought when I was invited to this workshop. So let's look at some of the stuff I participated in. And the first thing is eToys. And the network here, hopefully it works. Okay, it's faster now. By the way, I should mention, there's one powerful idea in computing, and that is simulation. Your computer can simulate other computers. This is a powerful idea, and this is one example. So the Squeak eToys used to be a native app, but Vanessa Freudenberg wrote a virtual machine in JavaScript, so we can run it in browser. And this is basically graphical blocks-based authoring system. And this car is following this script, so forward by 5 and turn by a little bit. And I can change the script, make the forward by step differently. But also you can look inside of the car. So basically this is the graphical representation of the car, and this is the symbolic representation of the car. So X, Y, and heading are changing. And one thing we used to do is to draw another object, maybe like a steering wheel of Mazda's car, and say keep. So this is the same kind of object, and I can look inside. Oops. What's going on? Seriously, do it. It often happens when some other device is connected. Okay, so I can look inside the object, and this one also has X, Y, and heading, and I can rotate this, right? So that would be the that would get you thinking that, oh, maybe I drag the heading of the steering wheel into turn by here, and then this is pathetic. Come on, do it. I can drive the car by rotating the steering wheel. So this kind of stuff is what we used to do. Again, but the main thing is the symbolic representation and graphical representation on one screen, and they are connected. And one more thing, so one of the things I did was to make a particle system. So instead of just one car, there are 2,000 red particles in this, and this script is saying that each particle moves a little bit, and then when it hits the green ceiling, it gives a little bit of momentum, and then go back. And the green one is trying to do constant acceleration falling. So basically, the 2,000 particles are pushing up. Green one is trying to fall, and it's showing the PV equal nRT gas law here. And one thing you can do is to reduce the, this happens sometimes too. Keyboard gets messed up. So you can reduce the number of particles. Okay, I will show a better one later. This is not good. But for this audience, one thing I'd like to mention is that so the eToys, so I didn't, of course, start eToys, but around like 2008, I assumed the core developer's role, and then that got me on some panel discussion at CHI, and the eToys was shipped on OLPC, so we had 1 million install base or something like that. And for this audience, one thing I'd like to mention in relation to Greenlight is this idea of 2D finite infinite scrollable pane. And I got the idea from this work, from the self-programming environment, and they called it Kansas. So Kansas is a large, as they say, Kansas is a flat space where many people live in. So that's why it's a scrollable infinite field. And there are many people join in the same session and do stuff together. And then, so Lex Spoon started a basically knockoff version in Squeak, and he named it Nebraska. And that's a little bit smaller, but still flat. And I'm not going to talk about this, but I myself did a shared space called Kanto. Kanto is a sort of flat space in Japan. So Greenlight was inspired by Kansas. And here, come on. I want to show the next thing, which is called Shedama. And, funny. So the Shedama is also a particle simulation, but the starting point was how do we teach science better? And in science is about making the invisible visible. For example, like air here, we cannot see the gas molecules. But we do not want to tell students that, you cannot see them, but you have to believe it just because I say so. That's the last thing we want to do. So what students should be doing is make like instruments to experiment it. And in my case, I made a vacuum cannon that shoots out ping pong ball, for example. You can watch this video later. But also, they can build a computer simulation model by themselves and then run it and tweak it to convince themselves that, oh, what's happening here matches with my mathematics. So that's what we wanted. And this system is for that. So let's see. So basically, it's based on turtle graphics. So, but there are a bunch of them. So in this program, basically, I say create 3,000 turtles, and each turtle has X, Y, and RGBA. And the fill random say, fill the X value of everybody between 0 and 512, and fill everybody's Y value between 0 and 512. And set color here says based on the X and Y, they get the different R and G value and draw. So 3,000 particles is hard to see, but I can say 30,000 or 300,000 or 3 million. And so there are 3 million particles, and this is live programmable. So this is often hard to do during the talk, but I am defining a new method, say move, that moves everybody toward this direction, and then loop says draw, oh no, the loop says move and draw. So I save it, and I loop, and everybody moves. So that's simple. And I'm switching to the next example. So there are 3,000 particles, and everybody has random positions. But here, each turtle has dx and dy. And that dx and dy are filled with random, like unit vector. So everybody has random direction. And if I run this step, so everybody is moving different directions, right? But what can be done here is to add the dy at every time. So I'm changing the program into like a gravity simulation on the fly. So that's Shedama. So here's another example. So this looks like a picture, but it's actually a set of particles, and their positions and colors are based on the pixel values in the original image. And this one also has a random direction. So if I say step, it has this dissolving effect. But this got me thinking, what if I use, instead of dx and dy, what if I use R and G and run it? So this means that yellow dots are faster than black dots. But one thing you can do is to change this to minus and accept. So it's like sticking your hand in the computer and changing the program. And this is, think. So people laugh and it's fun. But this is, I think computing should be fun. And if you have this kind of stuff, and if you have this kind of stuff, and also you have a bigger idea you want to communicate, I think having some instant, something triggers instant reaction is a great way to convey your bigger ideas, actually. So let's see, actually, one more thing. Oh, I forgot how this is actually implemented at all. So the idea is that this is live programmed, but my programming language here is translated into the shader language. So program is running on the GPU here. So it's running at the GPU speed, but I'm modifying the GPU code on the fly. So this is a game of life. But one thing, for example, you can do is to change the program while it's running. Maybe add a different case. And this is called high life variation. And you can experiment like game of life without restarting your simulation. You can change the condition and program while it's running. And I like this kind of sort of the interactivity and live programmable aspect of things. And that was sort of the several years ago. But we started a startup called Croquet. And so this was about providing a library so that people can make their collaborative applications. And we call it Croquet OS. And you might say, oh, it's just a library. Why do you call it an OS? But once Weizmann said that an operating system is software that manages space and time. And the Croquet is based on the logical time-based execution, so it's managing time. And space is like your data. So we said, oh, yeah, it's on OS. So that's sort of the marketing, but I embrace that. And you can write your own applications by using the software. Like the green light is written on top of Croquet. So the network part was done by Vanessa Freudenberg and with help from Alan Lanza and under David Smith's lead. And I didn't do much of the network part, but I wrote many applications on top of it. And yeah, I'm not gonna talk about how it works. One thing, going back to the green light, that's one example of Croquet, is that this is a web-based app. So you can embed other web pages. And I just embedded Google Docs. This is a real Google Docs. But when you are trying to collaborate with somebody over Zoom, and let's say you are trying to write a little document together, what you might do is to send a link to a Google Doc, and maybe send other links for the supporting materials and like references. But 5 minutes in, you start fishing. Oh, where's my Google Docs tab? And where's my other document? You have to find it among your 100 browser tabs. But in Greenlight, I have the confidence that on Marcel's screen, he's also seeing the Google Docs on the right and this document on the left. And I can point here and say, hey, Marcel, what do you think of this picture? And he's typing. So this guarantees that we are seeing the same thing and we can work together. So that was sort of the little idea that Greenlight enables. And here, I want to show something else. So another network challenging test. But nowadays, web browsers can do quite a lot, including 3D stuff. So this is a shared 3D space, and it's supposed to load like in 3 seconds. Yours did, okay. It's loading, yeah, so and this is shared space, so I look back and, oh, Marcel is white rabbit, and he can move. Yeah, move a little bit, for example. Yeah, so it's a shared space, and yeah, let's explore. Oh, by the way, yeah, he can move, and by the way, so here's a crane, and I can tap, and this moves. And if you look at the swinging is really synchronized. It's like basically the exact same, at the exact same time, it's in the exact same state. So but let's explore. Oh, by the, yeah, it's fine. I will take you now. So I say gather, and I'm doing a guided tour. Oh, it looks like a factory for drones, and they are testing one here, and it's going in circle. And it's going in circle because that drone is executing this program. This is actually a collaborative text editor. Oh, yeah, Marcel, I'll take you again. That's fine. So basically, this says that when, so there's a method called step. And what step method here does is to schedule offshoot itself. So schedule itself 20 milliseconds in the future. So 20 milliseconds in the future, the same method will be executed. But while scheduling it, it rotates by a little bit and forward by a little bit. So that's why this drone is going. Okay. Like I said, half-working network is worse than no network. I can switch. Oh man, okay. So, but what I can do is to get basically the no-code tool here. And I can say duplicate. So when duplicate, the initialization part makes it start moving. So like this. And maybe I can delete the original. So they are going in circle because everybody is following the same program. But what if I change the forward by value from positive 0.03 to negative 0.03? So I edited a little bit, and I'm hitting Command S, and everybody moves. So exact same thing happens there. So code is data here. It's propagated to all participants. And as I was shown, I used to do particle systems with dots, but nowadays I do it with drones. But interesting, if you want to do this in Unity, for example, what you have to do is like if you find a little change to make, you do it on your computer, you build a new version of binary, you send it to your friend, and in the worst case, you might have some server components you might have to update. So make sure that your friend installs the new version, you install new version, and then restart the application and go back to the same place and test. And it's crazy. But in this environment, you can, again, stick your hand in the world and modify it, and the effect is immediate. So you are still with me, right? So let's explore a little bit more. And so so there's some suspicious door, and I opened it, and there's a physics simulation. Or some engineers must have too much free time. And if you look at the screen, this is a physics simulation, but we are not communicating the positions. It's only the time is sent around, and the bit identical simulation is running on his computer and my computer. And for example, Marcel can tap one of those stopped things, and it reacts. But when I was showing that gray rudimentary text editor to my ex-colleague, he said that, programmers are opinionated bunch. They are not gonna use that gray dull text editor. They have their own favorite editors, and they have to use them. And I said, okay, this isn't a research project. So what I did, hopefully this works. Huh? So what I did was to have a little, change, like what server, and I can write the program on my local disk, and that will be injected into the space. So let's say, and they have the different colors, right? And that's because I have a method called random color. Random color. And this one creates a random number and then computes the HSP and convert it to RGB. But let's say Marcel is a designer I am working with, and he would say, hey, Yoshiki, I don't need those random colors. I just need green ones. And I would say, okay. Then instead of computing something, I say 00FF00. And save. And now we only get green ones. And I'm not going to go. So unlike that rudimentary text editor, this is a real text editor. And I use Emacs on other times, but this is more familiar to you. But not only tweaking some parameters, I can make a big change. So what I do other times is to add a new shape, like a cylinder shape, just changing few lines. So you can do that kind of stuff with somebody in real time. So that's sort of that's why like live programming is even more important for in collaborative settings. You just do not want to restart your world when there are other people working in the same space. So, okay, so now I think I go into the conclusion part, but it has some stuff to talk about. Oh, one thing I forgot to mention when I was talking about the vectors and geometric algebra and notation. So one thing I've been doing is like using AI for certain stuff. But in my mind, designing like abstractions and notation should be done by humans. AI cannot do it. Like I said, like Maxwell's equations took like 30 years from the initial idea to the refinement. And you need some crazy people who think that, oh, this is good. I don't care what other people say, and keep going for 30 years with colleagues. That's how you might get a great thing. But AI is just looking at today's popular thing, and you should do this. So human should be in the loop in designing that kind of stuff. Yeah, that's an important message I wanted to say. So the last part, there are 8 pictures here, and the top row here is showing basically pictures of actual hardware, like form factor. And the bottom row here are analogies, or what it compares to. And so let's start from here. And from Engelbart's point of view, the mainframe computers were like railroads. It's clunky, like you cannot go places where you want to go. You cannot go places when you want to go. You need to coordinate with, you need to wait for other people, and you need to go like limited places. But for Engelbart, what they made was like an automobile. With a little bit of training, you can go wherever you want, whenever you want with your friends. So that's what he said about his computer. And the mouse is like a little volume knob of your car radio when he invented the entire automobile. So that's what he said. And as I said, like Rick Ryder's and Taylor's paper was the communication device, right? Computer's communication device. And it's a great analogy. It's just not for computing, but this new machine is a thing that connects people. So that's a pretty good analogy in my mind. But what stands out to me is Alan Kay's notion. Forget about like devices and cars and stuff. This is a new thing, and it's like a book. It's a new medium. And it's a book, but it's a dynamic book. So you can do stuff on it. But not only it's just a dynamic book, it's a meta medium, so that you can write stuff in the book, maybe in a program form, and you can change the way you communicate with other people. So it's a meta medium. So that idea of like writing stuff in the book and changing the book itself, in my mind, this vision hasn't been fully realized. Even though, this stuff, like a square form factor with flat panel display, that's still what we use. But this vision isn't here yet in my mind. Don't have fun yet. But when I do this storyline, natural question people ask is then, what's here? What's the form factor? And more importantly, what's the good analogy here? And then actually the form factor here is already here in many ways. or some of them. Like, our eyeglasses will be your computer. Like those light fixtures will be computers. Like your table will be a computer. And you may have a little thing at the corner of your room, and you say something, set a temperature or something, and you just say and something happens. So the computers are becoming invisible. That's why I don't have a picture here. It's invisible. But then more important thing is, what it compares to, what the analogy you want to use to describe it. And of course, I'm not a visionary, so I don't have a answer. In the analogies, there is no single answer. But I have analogies I don't like. And as I said, some computers let you just say stuff and something happens. So for some people, it's like servants or slaves. Computers are like slaves. But I don't like that. But when I thought of this, why do I even care if slaves are computers? They are not people. But what I don't like, I understand, is that not only the world filled with those slaves, what I am afraid more is those masters of those slaves. Those masters will delegate thinking and designing to their slaves, yet they pretend that they know stuff or they can think. And I am afraid of the world filled with those masters. So I want to make sure that that doesn't happen. It may happen. So that's the sort of the recent project I've been working on. It's a Mozilla-funded project. It has a local AI. So you have a box at your home and you do stuff. And my vision is like this, basically. It's a collaborative space, but there's an AI agent in the loop. And of course, we have big problems we have to solve, and one person cannot solve. So people have to work together, but people can use AI agents if they can, and they are not slaves here. They are sort of the participants, and they will help you to solve bigger problems. And that's what I want. And this image is I made up and looks stupid, but I can show this, hopefully. And probably you have seen this before. So this is Tony Stark and Bruce Banner working in the same room, assisted by an AI agent, Jarvis. Right? And if you remember, actually, they didn't solve a problem. Actually, they created the problem in this movie. But it doesn't matter. So if this visual bothers you, imagine nicer one like this. In my mind, those are basically equivalent. And that's what I want to try. And I don't have stuff to show on that yet. But hopefully sometime I can show some good stuff. And that's basically the end of it. So let's work together, and let's think better analogies together, and let's solve bigger problems together. Thank you.
Okay, thank you so much for this very nice keynote. Maybe we have time for a couple of questions. Are there any questions in the audience or online? No questions? Online, do we have someone online? No? Okay, so maybe I have a question because, again, so we usually, or at least in the work we have seen, sometimes we have to deal with people arguing okay, no, visual programming languages are better or textual programming languages are better. Do you see something concretely that you think okay, maybe we can come up with this different abstraction? You showed us some blocks, some text, something more in between?
Well, in between or the combination of them, that's probably what I'm thinking of. So first of all, text is visual. For most people, you look at it and understand it. It's not too different from stuff like this. Like, this is a visual program, Snap, but you can do vector operation in it. So it's not, they are not either or.
Yeah.
As you said, the best of both worlds should be possible.
Mm-hmm.
And that's what people should think about, in my mind.
Yeah.
And there are editors where you can edit from keyboard, but you can also use some pointing devices. And nowadays, you can of course think about talking about your program and do stuff.
Mm-hmm.
And eye gaze, many other things can be used, I think.
Okay, thank you so much. Do we have any other question?
Maybe one online.
Yes. Okay.
I was seeing that someone was writing.
Okay.
So probably it will be right.
Probably that will take a while.
Tom wrote something.
Okay.
Using JavaScript and Croquet.
Yeah, okay, there is one.
Do you have access to it?
Yeah, you're using JavaScript and Croquet. Are we moving to natural language exclusively in your future vision, or does it still involve structured language?
Yeah, I'm pretty sure it's going to be still the structured language, actually. Like, like formula. This is still a better form of expressing the idea crisply than saying it. Are you going to talk about this, for example, in English, and you are not going to be able to communicate even to humans, not to mention computers.
Okay, perfect. So I think let's thank Yoshiki again. Thank you so much for the keynote.